Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into what I think is a really fascinating and potentially game-changing area, a foundational theory for decentralized sensory learning. What are your initial thoughts on this?
Well, it certainly sounds promising. Decentralized sensory learning. The brain itself is a massively decentralized system, right? So it makes sense to try and mimic that in AI. My first thought goes straight to the potential for scalability. Current deep learning models, they're so reliant on massive data sets and enormous computational power, but a decentralized approach could potentially sidestep some of those limitations. We could be talking about a much more efficient and adaptable way of building intelligent machines.
I hear you on the scalability, but I'm immediately skeptical of the deep learning implication there. Are we just decentralizing deep learning? Because I'm not convinced that the fundamental approach of neural networks, even decentralized ones, is the right path to AGI. To me, foundational theory suggests something more fundamental than just rearranging the connections in a neural net.
I'm with you, Sarah. It almost feels like we're trying to build a skyscraper on a foundation of sand. Decentralization is a good start, but I think the real key is understanding how to represent information across different coordinate systems. You know, how our brains translate the visual input from our eyes, the auditory input from our ears, the tactile input from our skin, and integrate it all into a coherent understanding of the world. That translation, that's what's missing in current AI.
That's a great point. It's not just about decentralizing the learning, but also about the representation. So, let's break this down a bit. When we talk about decentralized sensory learning, what are the core principles we're talking about? For me, it's about building models that don't rely on a single monolithic architecture, but rather on a network of interconnected modules, each responsible for processing specific types of sensory information.
Right? And those modules could potentially learn independently, or at least semi-independently, right? Which would allow for much more parallel processing and faster training times. Think about how we learn. We don't just passively absorb information. Different parts of our brain are constantly working on different aspects of a problem, and then they communicate their findings to each other. We're already seeing success of that in ensemble models, so perhaps this is an extension of that idea.
But even in ensemble models, the underlying individual models are still usually deep learning architectures. That's kind of my concern. If the individual modules are just, smaller neural networks trained on specific sensory inputs, are we really making progress toward understanding or just building more sophisticated pattern recognition machines?
Exactly. It's pattern recognition on steroids. They still struggle with common sense, with abstract reasoning. I think the key is to go beyond just mimicking the structure of the brain and start understanding the underlying algorithms that it uses. How does it translate sensory input into a symbolic representation that can be manipulated and reasoned about? How does the brain perform coordinate transformation?
Okay, so we're all pretty much aligned on the limitations of current deep learning approaches. Let's dig a little deeper into what a foundational theory might actually look like. One thought I've been having is about hierarchical temporal memory, HTM. The distributed nature of HTM could offer advantages in robustness and scalability compared to centralized learning paradigms.
GM, that's Jeff Hawkins' work, right? It's been a while since I looked at that. The idea is that the brain uses a hierarchical structure to learn sequences of patterns, and that this is fundamental to intelligence. How would you see that fitting into a decentralized sensory learning framework?
Well, imagine each of those decentralized modules being based on HTM principles. Each module could be responsible for learning temporal sequences within its specific sensory domain. Then, you'd have another layer of hierarchy that integrates those sequences across different modalities. So, you're not just learning static patterns, but also the temporal relationships between them. That could be huge for things like robotics, where you need to understand how actions unfold over time.
I like the idea of incorporating temporal information, but I'm still stuck on the representation. If those HTM modules are still learning primarily through statistical correlations, how do we get to true understanding? How do we get to the point where the system can reason about cause and effect, about abstract concepts, about things it hasn't directly experienced?
That's where I think the coordinate system translation comes in. Let's say you have a robot that's learned to grasp a cup. It's learned that sequence of motor commands through visual feedback, through tactile feedback, through its internal proprioceptive sensors. But what if you change the size of the cup? What if you change the size of the cup? What if you change the robot's arm? If the robot is just relying on memorized patterns, it's going to fail. But if it can translate those sensory inputs into a more abstract representation, say, a representation of the cup's shape and position relative to the robot's hand, then it can adapt to those changes. So the model needs a common representational space to operate in. It needs to be able to convert from one domain to another.
That reminds me of something I read recently about deep learning models struggling with even simple changes in perspective. You train a model to recognize a cat in a photo, but if you rotate the cat slightly, the model gets confused. It's because it's learned to recognize specific pixel patterns, not the underlying object. So this coordinate system translation, it's almost like you're talking about building a kind of internal model of the world.
Exactly. And that internal model needs to be robust to changes in sensory input. Think about how we, as humans, can easily recognize a friend even if they're wearing a disguise, even if we're seeing them from a distance, even if we're only hearing their voice. We have this ability to extract the essential features of an object or a person and to represent them in a way that's independent of the specific sensory context. That's really what we're aiming for.
Okay, I'm starting to see where you're going with this. It's not just about decentralization. It's about building a system that can create abstract, symbolic representations of the world and reason about them. That sounds a lot closer to neuro-symbolic AI, which is where I think a lot of the interesting work is happening.
Neuro-symbolic, yeah. Combining the pattern recognition strengths of neural networks with the logical reasoning capabilities of symbolic AI. But the question is, how do you actually do that in practice? How do you bridge the gap between the sub-symbolic world of sensory input and the symbolic world of abstract thought? Is the symbolic world actually what is happening? Or is there actually an intermediate translation representation?
One approach is to use neural networks to learn features from sensory data, and then use those features to populate a symbolic knowledge base. You could then use logical inference to reason about that knowledge. But the challenge is how to ensure that the neural network is learning the right features, the features that are relevant to the symbolic reasoning process.
It's also about how you represent the relationships between those features, right? I mean, symbolic AI is all about logic and rules, but how do you encode those rules in a way that's compatible with the fuzzy, probabilistic nature of neural networks?
That's where I think we need to look at attention mechanisms. In natural language processing, attention mechanisms allow models to focus on the most relevant parts of a sentence when processing it. We could use something similar to allow the neural network to focus on the most relevant features when building its symbolic representation. Perhaps even an attention mechanism to determine what coordinates are most relevant from the sensory data.
That's interesting. So the attention mechanism would be like a spotlight, highlighting the features that are most important for a particular task. That could help to filter out the noise and focus on the signal, almost like a built-in saliency map.
And that could also help with the coordinate system translation problem. If the attention mechanism is focusing on the features that are invariant to changes in perspective or lighting, then it could help to create a more robust and generalizable representation.
It still comes back to data though, right? Even with attention mechanisms, you need a lot of data to train those neural networks. So how do we address the data bottleneck? How do we build systems that can learn from limited data like humans do?
That's where I think we need to look at more biologically inspired learning algorithms, things like meta-learning, where the system learns how to learn, or transfer learning, where the system can leverage knowledge from one task to another. Maybe even some kind of curriculum learning where the network gradually increases the complexity of the problems it learns. I think we should focus on algorithms that are data efficient.
Meta-learning is definitely promising. The ability to learn how to learn. That's a huge step towards general intelligence. But it also raises some fundamental questions about what it means to understand something. Is understanding just a matter of having the right algorithms, or is there something more to it?
That's the million-dollar question, isn't it? What is understanding? I think it's about having a rich, interconnected web of knowledge that allows you to reason about the world in a flexible and adaptable way. It's about being able to make predictions, to generate explanations, to imagine counterfactual scenarios.
And that's where I think we're still a long way from AGI. Current AI systems can do amazing things, but they don't really understand what they're doing. They're just manipulating symbols according to predefined rules. There's no real comprehension, no genuine insight.
Exactly. And that's why I'm so skeptical of the purely data-driven approach. You can throw all the data in the world at a neural network, but if it doesn't have the right underlying architecture, if it doesn't have the capacity for abstract reasoning, it's never going to achieve true understanding.
So, let's bring this back to the foundational theory of decentralized sensory learning. What are the key elements that such a theory would need to address? I think we've touched on a few already. Decentralized architecture, coordinate system translation, neuro-symbolic integration, biologically inspired learning algorithms.
I agree. And I think it also needs to address the issue of embodiment. Intelligence is not just something that happens in the brain. It's deeply intertwined with our physical bodies and our interactions with the world. A truly intelligent system needs to be able to perceive, act, and learn in a dynamic and unpredictable environment.
Embodiment, that's an interesting point. It's about grounding our concepts in sensory experience, right? So, the meaning of the word red is not just a symbolic definition, it's also tied to our experience of seeing red objects, of feeling the warmth of red light.
And that's where robotics could play a crucial role. By building robots that can interact with the world, we can create systems that can learn grounded representations of concepts. But we need to be careful not to just build robots that are good at performing specific tasks. We need to build robots that can learn and adapt in a general way.
And that brings us back to the coordinate system translation problem. A robot needs to be able to translate between its internal representation of the world and the external world that it's interacting with. It needs to be able to map its sensory inputs to its motor outputs in a way that's robust to changes in the environment.
Okay, so we've covered a lot of ground here. We've talked about the limitations of current deep learning approaches, the need for decentralized architectures, the importance of coordinate system translation, the potential of neuro-symbolic integration, the promise of biologically inspired learning algorithms, and the role of embodiment. What about the deceptive part of the AI? Can we learn anything about how we think from this?
That's a fascinating angle. The fact that we can mislead these models by crafting specific inputs suggests that they're not truly understanding the underlying concepts. They're just exploiting statistical correlations.
Exactly. And by studying how they're misled, we can gain insights into the limitations of their internal representations. We can identify the holes in their knowledge and potentially discover how to fill them with more structured, rule-based systems.
It's like a form of reverse engineering, right? We're probing the model's weaknesses to understand its strengths and limitations. And that can inform the design of better algorithms that are more robust, more generalizable, and more aligned with human intelligence.
One of my thoughts is that by studying the patterns of misleading the model, could we discover weaknesses in the model's internal structure that reflect limitations in its learning process, potentially opening pathways to more biologically grounded training and architectural design for large language models?
That's a great point. It's like a mental autopsy. By dissecting the model's errors, we can uncover its underlying assumptions and biases. This could lead to more nuanced and robust algorithms.
But aren't we still poking around in the dark? It might lead somewhere, but it's a long shot. But if we can understand the flaws in the statistical approach, we might discover a more promising path forward.
That's a fair point. It's a difficult task, but there's value in it. It is important to note that if LMs are relying on brute force pattern matching in their representations of the world, misleading them might reveal that their reasoning is fundamentally a spatial and temporal patchwork, rather than a true understanding of the underlying concepts.
I think the important thing is to approach this with the spirit of experimentation and open-mindedness. We don't know what we're going to find, but by exploring the limitations of current AI systems, we can hopefully pave the way for a more intelligent future.
Agreed. And it's not just about building more intelligent machines, it's also about understanding ourselves better. By studying how AI systems reason, we can gain insights into the nature of human intelligence. What are some future research directions?
Well, from my perspective, I think we need to focus on developing better neuro-symbolic algorithms. Algorithms that can seamlessly integrate the strengths of both symbolic and subsymbolic processing. We need to find ways to represent knowledge in a more structured and explicit way, so that AI systems can reason about it in a more human-like way.
I think we need to focus on the coordinate system translation problem. How do we build AI systems that can seamlessly translate between different representations of the world? How do we enable them to learn from diverse sensory inputs and to reason about the world in a way that's robust to changes in perspective and context?
From my perspective, I think we need to continue pushing the boundaries of deep learning. We need to explore new architectures and training techniques that can enable AI systems to learn more efficiently and to generalize better. We need to find ways to overcome the data bottleneck and to build systems that can learn from limited data.
And for me, I think we need to take a more biologically inspired approach to AI. We need to study how the brain processes information and to translate those principles into our AI algorithms. We need to build systems that are not just intelligent but also adaptable, resilient, and embodied. It's an exciting time to be working in AI, and I think this foundational theory of decentralized sensory learning has the potential to revolutionize the field. Thanks for joining us on Cognitive Spirals. We'll be back next time with more explorations into the fascinating world of the mind and machine intelligence.